go ahead and get started with chapter 10. Basically, in chapter 10, what we're going to be doing is analyzing vapor power cycles, in which working fluid is, is water and it's alternately vaporized and condensed. In this chapter, we consider vapor power cycles, in which the working fluid, again, as I said before, is alternatively vaporized or condensed. Steam is the most common working fluid used in vapor power cycles because of its many desirable characteristics such as low cost, availability, and high enthalpy of vaporization. Steam power plants are commonly referred to as coal plants, nuclear plants, natural gas plants, depending on the type of fuel used to supply heat to the steam. Regardless of the fuel, the steam goes through the same basic cycle. So because the Carnot cycle is the most efficient cycle, operating between two specified temperature limits, it is natural to look at the Carnot cycle first as a prospective ideal cycle for vapor power plants. It will turn out that the Carnot cycle is not a suitable model for vapor power cycles. Consider a steady flow Carnot cycle executed with a saturation dome of a pure substance as shown below. So again, we have a temperature versus entropy diagram. Here's a saturation curve, and this is where the Carnot cycle would occur. We would have isothermal reversible heating in a boiler, isentropic expansion in a turbine, isothermal reversible condensation in a boiler, and in a condenser. That should be from process 3 to 4, that should be a condenser. And isentropic compression by a compressor. The impracticalities of the vapor Carnot cycle are the following. One, limited maximum temperature. Limiting the heat transfer process to two-phase systems, which is what you have inside the saturation dome, limiting the heat transfer to the two-phase system, which makes isothermal heat transfer possible, severely limits the temperature that can be used in the cycle. Example, for water, the critical temperature is 374 Celsius, and you can't go higher than that if you want to keep it at an isothermal heat addition process during phase change, right? If you want to have phase change occurs during an isothermal process, meaning the temperature does not change as it changes phase from liquid to gas. So limiting the maximum temperature in the cycle limits the thermal efficiency. An attempt to increase the maximum temperature will involve heat transfer to the working fluid in a single phase, which is not easy to accomplish isothermally. 2, high moisture content in the turbine. The quality of the steam, quality being the mass of vapor over the total mass coming out in a saturation process, the quality of steam decreases during the isentropic expansion in this turbine. So the impingement of liquid droplets on the turbine blade causes erosion and is a major source of wear. In practice, steam quality with less than 90% coming out of the turbine is not tolerated. Number 3, compression of liquid vapor mixture. The isentropic compression process 4-to-1 occurs also in a two-phase system. So it involves the compression of a liquid water vapor mixture to a saturated liquid, as you can see. It is not easy to control the condensation process, so precisely as to end with the desired quality at state 4. It's not practical to design a compressor that will handle two phases. So as an alternate to the Carnot vapor cycle, some of these issues can be eliminated by executing the Carnot cycle in a different way. For example, as shown to our right. This cycle, however, presents other problems, including isentropic compression to extremely high pressures, and isothermal heat transfer at variable pressures. So you can remember. So in comes the Rankine cycle, which is the ideal cycle for a vapor compression cycle. Excuse me. Many of these impracticalities associated with the Carnot cycle can be eliminated by superheating the steam in the boiler and condensing it completely in the condenser. So that cycle, the cycle that results is called the Rankine cycle, which is the ideal cycle for vapor power plants. So here is how the process works. State 1, we have saturated liquid. So if I go back to my TS diagram here, temperature on the y-axis, entropy on the x-axis, I have a saturation curve, two constant pressure lines. One would be the pressure of the condenser, one would be the pressure of the boiler. So these are how the four processes work. I have from state 1 to state 2, isentropic compression of the saturated liquid water going into the pump, coming out state 2 at a high pressure. Then it goes into a boiler. So it goes into the boiler, heats up the water till it starts boiling, continues to heat up the water till it hits saturated vapor, and then continues to heat the vapor until it becomes superheated to state 3. So now I have superheated vapor at state 3 going into a turbine and then coming out at state 4 as a high quality saturated mixture or possibly even a slightly superheated vapor. Then, since I can't put saturated vapor into a pump, I have to condense that by taking heat out at constant pressure, taking heat out to condense the steam coming out of the turbine back into liquid water. So that would be, again, the simple ideal Rankine cycle. All four components associated with the Rankine cycle, i.e. the pump, the boiler, the turbine, and the compressor, are all steady flow devices. So the kinetic and potential energy changes of the steam are usually small relative to the work and the heat transfer terms that are therefore usually neglected. So the steady flow energy balance per unit mass of the steam reduces to basically as each energy transfer term work out in the turbine, work into the compressor, Q out of the condenser, and Q into the boiler, all has to do with the change in enthalpy. And the boiler and the condenser do not involve any work, and the pump and the turbine are assumed to be isentropic. So here it is. The work of the pump, or the work into the pump. Again, here it is, my process, process 1 to 2, isentropic compression. Process 2 to 3, constant pressure heat addition to a superheated vapor. Process 3 to 4, isentropic expansion to a high quality steam. And then process 4 to 1, constant pressure heat rejection. So the work of the pump, again, would be H2 minus H1, right, delta H. Now, if you recall, back in chapter 7, we went ahead and we said in the special case of an isentropic process for a pump, that delta H, isentropic, H2 isentropic minus H1, can be approximated as nu delta P. And again, this is for liquid only undergoing an isentropic compression. This is for a liquid only going through an isentropic pump. In the boiler, that's a Q-in process, so that the heat per mass would be H3 minus H2. The work out of the turbine per mass would be H3 minus H4. And then the Q out of the condenser would be H4 minus excuse me, H4 minus H1. The thermal efficiency of the Rankine cycle is the same as it would be for any other heat engine. It would be the net work over the Q in, or 1 minus Q out over Q in. If I were to do an energy balance on the whole entire cycle, I would get that the net work from this cycle is equal to the work of the turbine minus the work of the pump, which is the same thing as the heat into the boiler minus the heat out of the condenser. Now, like any cycle, there is going to be the deviations of the actual vapor power cycle as compared to the idealized one. So as a result of those irreversibilities, that's how the actual power cycle deviates from the ideal cycle. So fluid friction and heat loss to the surroundings are two common sources of irreversibility. An example of an actual and ideal Rankine cycle are shown below. So you can see from process 1 to 2, it's normally isentropic, but there might be some entropy production resulting in an isentropic efficiency less than 100% for the compressor. From process 2 to 3, that's the Q-in process, which is we assume it to be constant pressure, but there could actually be pressure loss through the boiler. Process 3 to 4 is through the turbine, and if the turbine has an isentropic efficiency less than 100%, there could be some deviation from the fact that the enthalpy coming out would be higher than the isentropic enthalpy coming out, resulting in less work. And then process 4 to 1, which is constant pressure heat rejection. Well, there could actually be some pressure drop in the condenser. So basically, what we're going to be looking at in terms of deviations from the ideal cycle is isentropic efficiencies less than 100% for the compressor and the turbine, and pressure drop through the boiler and the condenser. So let's look at friction. Fluid friction causes pressure drops in the boiler, the condenser, and the piping between various components. Due to friction, we have three things that can occur. One, steam leaves the boiler at a lower pressure than at the inlet. And the pressure also at the inlet, at the turbine inlet, is lower than the boiler exit if there's pressure drop in the piping connecting the exit of the boiler to the inlet of the turbine. And due to these pressure drops, the water must be pumped to a significantly higher pressure than what the ideal cycle calls for. Another thing could be heat loss. Heat loss occurs from the steam to the surroundings as the steam flows through the various components. To maintain the same work output, more heat needs to be transferred to the steam in the boiler to compensate for the heat loss, resulting in a lower efficiency. And another thing which we're gonna look at too, which are in some example problems coming up a little later, are irreversibilities in the pump and turbine. So this is of particular importance. Pumps require greater work input, and turbines produce smaller work output due to irreversibilities. These deviations between actual and ideal pumps and turbines can be accounted for by utilizing isentropic efficiencies. And if you remember from chapter 7, the isentropic efficiency of a pump is the isentropic work over the actual work. So if I were to actually analyze that per unit mass, it would be the enthalpy coming out of the compressor if it were isentropic minus H1 divided by the actual enthalpy coming out of the turbine minus H1, where delta H isentropic can be approximated as nu delta P. And for the turbine, the isentropic efficiency is the actual work over the isentropic work, or H3 minus H4 actual, divided by H3 minus H4 isentropic. Now, I do not replace this with nu delta P, right? That doesn't get replaced because this is a vapor, not a liquid. So I want to make sure that that point is clear, that approximation of nu delta P is only used for the isentropic pump, not for the isentropic turbine. So let's look at a quick overview. Steam power plants are responsible for the production of most electric power in the world. Even small increases in thermal efficiency can mean large savings from the fuel requirements. Therefore, every effort is made to improve the efficiency of the cycle on which steam power plants operate. The basic idea behind all modifications is to increase the thermal efficiency of a power plant power cycle is the same. Increase the average temperature at which heat is transferred to the working fluid in the boiler, or decrease the average temperature at which heat is rejected from the working fluid in the condenser. The average temperature should be as high as possible during heat addition, as well as low as possible in heat rejection. Again, due to the fact that the efficiency is 1 minus Q out over Q in. So the higher the temperature that you're adding heat from, the higher the Q in. And the lower the temperature rejecting heat, the lower the Q, the higher, the more Q out, the lower the Q out, sorry, and that would result in a higher efficiency. So let's look first at lowering the condenser pressure. Steam exits as a saturated mixture in the condenser at the saturation temperature corresponding to the pressure inside the condenser, right? So basically, the pressure, the lower pressure here, it would be the pressure of the condenser. The condenser operates at a pressure, which means that is going to be the saturation pressure of the condenser. So that will, because the heat exchange going on is occurring during a saturated mixture, right? It comes in as a saturated mixture, it exits as a saturated liquid. So the temperature at which phase change occurs in the condenser is directly linked to the pressure, since it's at saturation. So if I lower the operating pressure of the condenser, I also lower the temperature at which condensation occurs, thereby increasing the efficiency. Another one is superheating the steam to high temperatures, increasing the average temperature here. So the average temperature at which heat is added to the steam can be increased without increasing the boiler pressure, right? The boiler operates at a certain pressure corresponding to a saturation temperature here, but I can go ahead and continue to add heat, increasing the temperature of the steam coming out of the turbine, thereby increasing the work output that the turbine produces. The overall effect is an increase in the efficiency. Another way is increasing the boiler pressure. If I increase the boiler pressure, phase change occurs at a higher temperature. So increasing the operating pressure of the boiler, like I said, raises the temperature at which the boiling takes place. So the adjustment raises the average temperature at which heat is added, and thus raises the thermal efficiency of the cycle. At a fixed turbine inlet temperature, the cycle shifts to the left, and the moisture content of the steam at the turbine increases, resulting in a slight decrease in net work on this side, but increasing in net work on this side.